Let's take a look at this example involving two vector-valued functions. So our first vector-valued function is little r of t, which is 2 minus e to the t, 4 minus e to the negative t. And it's only defined on the interval ab, which is from 0 to natural log of 10, including 0 and natural log of 10. Capital R of t is 2 minus t, 4 minus 1 over t on some interval cd that we don't know yet, which we're going to look at on number 1. So what we're trying to do on number 1 is find the interval cd over which the capital R trajectory is the same as the little r trajectory over AB. So just to get a feel for what's happening here, let's take a look at Desmos. So here I've got the equation for little r of t, and it's only defined between 0 and natural log 10, including. And we get this little piece right here. Okay? So now, if we want to look at capital R of t, which is right here, so I'm going to turn this on, that's all of capital R of t. Okay? All of that. So we can see that these two functions do overlap. And so the question is, for what values of t would capital R of t trace this same path that we see for little r of t that's defined between 0 and natural log of 10? All right, so if we're looking for the values of t on this blue graph, that will produce this little piece of the red graph, that little piece right there. All right, so let's go back over here. What we really need to do then is figure out, the coordinates of those endpoints on little r of t. All right, so we know that little r of t is defined between 0 and natural log of 10. So let's start with t equals 0. So at t equals 0, let's find little r of t, or little r of 0. Let's write that. And plug 0 in and see what the coordinates of that point are. So we're going to plug 0 in for t. So e to the 0, and then 4 minus e to the opposite of 0. So that's going to give us 2 minus 1, which is 1, and 4 minus 1, which is 3. All right, so now let's plug in the other endpoint, which occurs when t is the natural log of 10. So let's see what we get for that. 2 minus e to the ln 10, and 4 minus e to the opposite ln 10. All right, so if you remember this property, e to the ln of something is just that something. So this is going to be 2 minus 10. And we do have a negative here. So I'm just using I'm thinking about properties here of natural log of 10. We could bring that negative 1 up. So that would be the same as natural log of 1/10. So e to the ln of 1/10 is just going to be 1/10. All right, so 4 minus a tenth. 4 minus a tenth is going to give me my coordinate there. So we have -8 and 3.9. So let's go over to Desmos and see if those track with what we have. Let's see if we can. So to see the points, I have this set up as a point, and then I have this slider S here. Okay, so it looks like this point right here, when t is 0, is 1, 3. That looks good. And when t is natural log of 10, whatever that decimal is, we get -8 up 3.9. So that looks good for the values that we got over here. So now what we want to do is we want to find c and d so that these are the endpoints for capital R of t. All right. So we want to find some value of t. I'm going to look at capital R of t over here. We want to find some value of t so that 2 minus t, 4 minus 1 over t comes out to be these endpoints, 1, 3. All right, so we could set up a little equation, but I think we could look at this and see that t is 1, right? 2 minus 1 is 1, 4 minus 1 over 1 is 3. So in this case, we get t equals 1. And then we want 2 minus t, 4 minus 1 over t to come out to be -8, 3.9. All right, so I need my first component here, 2 minus t, to be -8. So that's going to be 10. And I need my second component. Let's just double check it. If I have t as 10, I'm going to get 4 minus a tenth, which is 3.9. So you might be asking, well, what happens if these two things don't come out to be the same? Well, what that would mean is that these two vector-valued functions don't necessarily follow the same trajectory anywhere, especially on this piece that we're looking at. If they follow the same trajectory for certain values of t, then these are going to come out the same for both components here. So that tells us that we need our interval to be from 1 to 10. So that's going to be our CD interval. So let's go check this out in Desmos. All right, I'm going to turn on the vector valued function there. And let's put the t values in from 1 to 10. All right, there we go. See, we're getting the same piece. That's awesome. All right, so now let's turn on this point. I have the slider S, which is acting as t. I had to create a different variable here so that it would plug S in for the point and trace the point. So let's start, let's see, let's put this at 0 to 10. That should work, right? So we can follow our points here. Okay, so they're not, the points are not at the same place at the same time, but they do trace out the same piece of the graph, the same trajectory for a certain interval. And that interval is not the same for the two functions. And the points are not at the same place at the same time. It's kind of neat. They're not even going at the same velocity, right? Which we're going to look at here in a minute. We can see they're not traveling at the same velocity. So with that in mind, let's look at question 2, which is to find the velocity of both objects. So if you recall, the velocity is found by taking the derivative of the position vector. So we're going to take the derivative of r of t. So that's going to give us negative e to the t. Derivative of 2 is 0. Derivative of 4 is 0. And then we have minus e to the negative t, but we have to use our chain rule and take the derivative of the opposite of t, which is -1. So if we multiply that, we're going to end up with a positive there. All right, and so the derivative of the capital R of t function is going to be, what do we got here? -1. And then I think of this as t to the -1. Bring that down, reduced by 1 is going to be t to the -2, and those negatives are going to cancel out. So I think we're going to get 1 over t squared. So if we just look at these, we can see that little r of t, the velocity as t increases, especially the x component here, is going to increase exponentially in the negative direction, which we saw. We can go back at Desmos and look at that and see how that point was moving pretty quickly to the left. Whereas, you know, here I don't have things speeding up. I have x at a constant speed of -1, and my y component, as t gets big, is actually slowing down, which means the point is, you know, increasing in the y direction slower and slower as t increases. And we can kind of see that. Let's go back over here and look at this again. I could even, well, we can just look at it for these values. But I can also, you can see that red point, you know, really taken off in the negative x direction. That's that velocity as negative e to the t power as t increases, whereas the blue point's kind of slowing down, especially in the y direction, and then moving in the x direction, it's pretty constant speed. All right, let's take a look at number 3. Graph the speed of the two objects over the intervals. So remember, the speed is the magnitude of the velocity vector. So to find the speed, we need to find the magnitude of this velocity vector, which is going to be the square root of the sum of the squares of its components. All right, and the magnitude of this velocity vector. Now, what is this telling us? Remember, the magnitude is telling us the speed without regard to direction at a particular value of t. The speed. So we notice that in little r of t, it was a lot faster, right? We were getting a lot more speed. That thing was really moving to the left. And to the left part, we get that information from the velocity vector. We don't get that information from the speed. We'll get the speed, but we won't necessarily know that it's going to the left very fast. But we could see that from the velocity vector here, that negative e to the t. That x component is changing very rapidly, whereas the y component, as t gets big, this gets small, right? So that would tell us that it's going to be changing slower and slower in the y direction. All right, let's simplify this a little bit, make it a little bit nicer. What are we going to get here? E to the 2t plus e to the negative 2t. Can't simplify that. And here we're going to get 1 plus 1 over t to the 4th. All right. So let's go ahead and take a look at the graph of that. So I'm going to go to decimals to do this, but what we're going to do for the graph of this is more of a traditional xy, not a vector valued function. So I'm going to do the input is the value of t, and then the output is the speed. The output is the speed at that value of t. So it's not really a vector valued function. It's more like a function of t. Okay, let's go take a look at that. This is still rolling over here. So I have those here. So here is the speed, the input t. So at time t, this is my speed. And I'm just doing it on this interval from 0 to natural log of 10. So what's happening to the speed? It's increasing rapidly, right? And we can see that. Let's take these off and just look at this little r function. I should change it so it's speeding up, right? That's what this is telling me here. Okay, let's look at the other one. Turn these off. And let's go look at capital R of t, the points on capital R of t, and the speed. What's happening to the speed from 1 to 10? It's decreasing and then sort of leveling off, which we definitely saw, right? We saw sort of a constant speed there, which we would expect because the x value of the velocity vector was -1, which is constant, and the y value as t increasing was approaching 0, right? So it's basically approaching a constant speed headed to the left. So I think that's a pretty nice example of looking at two vector valued functions and really thinking about how t affects where is the location of the point, how the velocity vector affects the speed and direction of the point, how that point is moving, that maps out the trajectory, and then also just thinking about the speed as a scalar as t increases over a certain interval.